further, let's get this straight. It's not a how to play guitar lesson, it's not a concert, and it's not a lesson on music theory, all right? It's a little discussion about the physics of stretched strings and the vibrations that they produce, which we, like to call sound. So, with that in mind, no expecting any great performances, and I'm not going to embarrass myself by making out like I'm a musician, okay, right? I'm a physicist, and I happen to like to learn to play the guitar, which means I have here this very sophisticated piece of equipment that we can use to explore the relationship between the length of a string and the vibrations that it produces. And in the background here, you can see we've got a computer which we're going to hook up to a sound collecting device here, a little sound probe, which is basically just a little microphone, and it's going to enable us to record sounds and actually look at the shapes and forms of the sound waves and what kinds of vibration frequencies the string is actually producing. And at the same time, we can look at the strings and say, well, how much do I shorten a string and what kind of note do I get out of the other end? And so what we're going to do is look at the guitar first and just point out some very obvious features that make it ideal for this kind of experiment. So the guitar has 6 strings, right? 2, 3, 4, 5, 6. And they're all the same length, right? They're all about the same length, they're all about 1 meter long. I guess we could measure it with a ruler if we wanted to, but they're all about the same length, and they're all held under tension by these little tuning pegs at the top. They're all under about the same tension, which is an interesting fact. Think about this. If one string was under much more tension than the others would all go slack. So when you tune a guitar, you change the tension of the strings, but basically they all have about the same tension. So what else is different about them? They sound different. So you notice that the bottom string, which is on top here, it's a very low note. This is a very high note up here. Let's look up close at the guitar. What's different about those strings? Well, the string here that makes this very high sounding note, it's very, very thin string, very lightweight. This low note here, it's a very thick, heavy string. They're made of steel. So the difference between this string and this string, the tension's about the same, the length is the same. What's different about them is the weight of the string they're made out of. So evidently, the heavier the string, the lower the note. Isn't that interesting? And those of you who are musical will notice that there's something that sounds kind of similar about those two notes, even though they're not the same note, but we'll get to that in a minute. Alright, that's enough of the guitar. Now we're going to have a quick look at the computer and the data capture systems. I'm going to take the guitar off, put it down there, and bring the camera over. Alright, so we start data collection, make a sound with the guitar, let that sound die away, stop it. Alright, now the piece we're going to analyze this piece in here, because I was kind of making a lot of noise here and then I was talking down here. Okay, so here's this computer representation of the sound from the guitar when you're swinging the string like that. We can basically see the amplitude of the sound getting bigger and then dying away, just like you hear it, right? Starts off loud, dies away. So that's what we're seeing here with this shape on the graph. Now if we zoom in, we're going to be actually able to see the individual sound waves, which is kind of a neat thing. So let's try that. So if I zoom in, which is what I'm doing now, just picking a piece of the data, zoom in, you can see that the data consists of all these little up and down movements. So here we are, you can probably see that. All these little up and downs, and every up and down looks pretty much the same as every other one. And if we were to look and say, well, how long does it take to go from, one of these peaks down into a trough and back up to a peak, we could measure that, and we could see, how many seconds it is. See if I can actually do that. So we're going to take this little thing here, we're going to put it at the top up here, and we're going to measure from here all the way to, say, here. Let's see if we can do that. So there we go, and the length of that little line there is 0.008 seconds. So the time for one complete oscillation of this sound wave is 0.008 seconds. If you put it in your calculator, you'll be able to see what the frequency is, how many of those up and downs do we get every second. And that will tell you what frequency the string is actually oscillating at. So let's now zoom out, and so that we're no longer zoomed in. And we're going to make a special analysis of this. We're going to do something called a Fourier transform, which is going to tell us what frequencies are actually present. So let's see if we can do that. So select run 1, drag it into FFT down here. And here is our spectrum, sound spectrum. I'm going to change some of the parameters on it a little bit. Just decreasing the bin size so that we can actually see the individual. You can see there's a whole bunch of different peaks in the spectrum. And these peaks correspond to frequencies that were actually in the sound wave. So like we saw from looking at the wiggly graph, that each sound wave took about 0.008 seconds for one cycle. And so from that you can calculate the frequency, how many of those per second. And so the computer is basically doing the same thing, but it's doing for all kind of little bumps and wiggles in the graph and averaging them all together over the whole sound clip. So we can see what are the strongest oscillations in there, and now we can use the computer to figure out what's what. We've got the strongest peak at 161 hertz. So 161 or 160 cycles per second. There's 160 if I get it right in the middle. It's about 160 cycles per second. We've got a vibration going on. And what have we got here now? What's this next one up? Let's see what this one is. This one is at 320. And the next one, right, about 399. Another one down here at about 555, 557, something like that. 724. If we go right back down, oops, I don't want that. Right back down here, what's this one? Got one here that is at 80 hertz.